Alrighty, welcome back to our topic 5 of antiderivatives and integration for AP Calculus AB. This is actually our second to last video lesson for this unit, and it is the second part of the Fundamental Theorem of Calculus. I think I mentioned before that some teachers will teach this part first and the other part second. Some people teach them both at the same time. I like keeping them isolated though. I think you gain a larger intuition of how this works if you already know the, quote, first part, end quote. So let's start with an opener. You're going to have to follow order of operations here, which means you're going to have to evaluate the expression inside the parentheses first, and then you'll take the derivative of that afterwards. So let's go ahead and see what you come up with for each of these, and then we will see how you did afterwards. Please don't forget that the derivative of a constant is 0. Ready, set, go. All right, we're back. Let's go ahead and work through these quickly to see how you did. Let's see, Fundamental Theorem of Calculus here. This is our part 1. We do the antiderivative of sine of t, which is cosine of t, and it's with respect to t, so we don't need anything else going on there. Then we evaluate that from 1 to pi. So that means we still need the derivative of the cosine of pi minus the cosine of 1. And although we know that the cosine of pi is -1, I actually don't, without a calculator, know what the cosine of 1 is. But I do know it's a number. And since we're being asked to take the derivative of all this, and this is all just a combination of different numbers, this is all just one big giant constant, I think the derivative here is 0. Easy. All right, let's try our next one. And if that helped you determine what you should be doing here, then you should probably pause and try the next two. You always want to try it on yourself before letting someone else do it for you. Okay, so here's our next one. We're again looking to take the derivative with respect to x. It's interesting noticing that this x doesn't match the t, but it doesn't have to, and there's a meaning behind this madness, I promise. So cosine of t, we've seen this before. This time we're going from 1 to x. Well, even though we're used to seeing the fundamental theorem of calculus where both of these are values, it doesn't change how this works. We substitute in x, we substitute in 1, and then we're looking better. Now, when we go to take the derivative of all this, the derivative of cosine of x is negative sine of x, I think. Oh, and have I been doing the antiderivative wrong this whole time? I have. Oh, that's all right. That's an easy fix, though. Just doing derivatives. The antiderivative of sine should be negative cosine because the derivative of negative cosine should be sine. So that's just going to change all of our signs here, but it doesn't really make it too much of a difference. There we go. Right? Even teachers can make mistakes. So this should be negative cosine. So this becomes negative cosine of x plus cosine of 1. There we go. And then the derivative of negative cosine is positive sine, and the derivative of cosine of 1 is still 0. And so we end up with sine of x. Awesome. Last one. Antiderivative first. Okay, antiderivative of this, well, is just negative cosine of t. Easy for me to do. X squared to x. Use that fundamental theorem part 1. So we end up with negative cosine of x minus, but there's already a negative, so it becomes a plus, cosine of x squared. And finishing this off, the derivative of negative cosine of x is sine of x. Derivative of cosine of x squared is negative sine of x squared times an extra 2x. And there we go. Okay, so what are we doing for today? Well, honestly, we already did it. We're really just going to learn a shortcut for what we did and then maybe gain a better understanding of what we just did in context of derivatives and integrals. So just a quick nice review. An integral, of course, a definite integral in this case, measures the signed area between a curve and an axis. The derivative measures the rate of change of a quantity, how fast something is changing, right? Therefore, on problem A, it's not a surprise that our overall answer was 0, because what we did here is we found the area between sine of x and pi and that is a specific number, right? This right here is a number. And then we said, how fast is that number changing? Well, it's not changing, it's a constant. And so the derivative of that constant is 0, because what are we measuring with this d dx? We're measuring how fast the area is changing with respect to x. Okay, so because the area was constant. However, on problems B and C, we don't have a constant area, right? The area from 1 to x is not constant. The area from 1 to x says start measuring the area beneath the graph of sine of t at 1, and then go until you reach whatever x value you substitute in. And I'm going to go ahead and show you a quick visual of this and try to explain what's happening here. So I have the integral from 1 to, let's pretend this is x up here. And currently I have my upper limit set at 1. So the area from 1 to 1 is 0. Not a surprise. I'm also going to show you the graph of sine of x. And currently there's no graph of sine of x because I'm going from 1 to 1, so there's just a point there that's somewhat invisible at this point. So here is 1. Let's see what happens as I move forward. Right? As I move forward, now we start with a graph. Let's go over to 2 maybe. Here is the graph of sine just from 1 to 2, and there is some sort of area between the curve and the x-axis. How much area? Well, according to my integral up here, there's almost an area of exactly 1, which is very exciting. So, as we, and jumping back here, as we're moving to the right, what or how would you describe the area that's up here? Is the area gaining or decreasing? And hopefully, as you see, as this graph goes to the right, the area is increasing because every bit we bring it to the right, we add on more area underneath. All right, we're going to get right about pi, right, 3.14, right about there, give or take, is our x-intercept, and it says the area is, well, in this case, it looks like it's pi over 2, give or take, half of pi, right? So anyways, our a value is right about pi. We're here. We have added on all this positive area. But what's going to happen once the graph dips below the x-axis? We're going to start adding on more area, but what do you remember about the area below the x-axis? Well, yeah, that area is negative, and so we should probably see this total area here start to shrink. And as we go forward, you see that area now is decreasing, 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 until we get to 2 pi. And then we start to increase. Now the area is getting positive again, increase, 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 and now we're decreasing, and so on and so forth. So this function from 1 to x is showing us, or rather, if you treat this as a function, it's explaining how the area is increasing. Okay, so when we're taking the derivative of this, or the derivative over here on b, the derivative of this area function, the answer to the derivative of the area function, the sine of x down here, is explaining how fast the area underneath the graph is changing. And it matches up with this x. For example, if we wanted to pick right at 2, right? 2 is as this graph is still adding on more area, and I wanted to see how this was changing. Well, I would just do sine of 2, and it would tell me that currently the area is increasing at a rate of 0.909, right? I'm using this equation to measure how fast the area underneath this graph is changing. Now, you might be looking at this saying, well, this is the same equation as this, and in fact, that's more of a coincidence than anything else, and we're going to maybe argue later on it's not a coincidence, but we're going to treat sine of x as the derivative of this area or accumulation function. And yes, right now it does look very, very similar, even though the variable has switched. And what we're going to look at today is, does that always happen, or is there something else going on? And you can already see the answer to that in C, right? This function down here in C is describing how the area is changing if you square an x value and then you go to an x value, right? It says you have to use this more complicated function, which is certainly not the same as the function inside. But are they related? All right, filling this in and then getting to our fundamental theorem part 2. The derivative of these area functions measures the rate of change of the area of a function. So here we go. Fundamental theorem review. You need to have memorized the Fundamental Theorem of Calculus part 1. And it's fairly easy, right? It's just the part that tells us, apparently I'm having trouble with my letters today, that we do the antiderivative first, and then we substitute in the upper limit and subtract off the lower limit. It's worth mentioning, too, that this integral does not have to go least to greatest. One of the coolest things about the fundamental theorem is if this went from 5 to -1, which is somewhat backwards for us, that's okay. If this is 5 and -1, you substitute it in here, it will all take care of itself. And so you don't need to worry about switching the limits. You still can, and you'll get the same answer. But either way, just something to consider. Okay, so what does the fundamental theorem do? Well, the fundamental theorem gives us a way to find the area underneath any integrable curve. But we discussed how the fundamental theorem relates areas and derivatives together. And since calculus also has that differential calculus, that derivative branch, then we are also going to see if there's a shortcut that lets us study how fast the area of a function changes, essentially the derivative of the area. So let's begin. We've already seen the area or accumulation function where we have an input, which is the upper limit of integration. We have this t, which is a dummy variable. You can pick anything you'd like. And we say that as you change x, it tells us. So as you change x, it tells us what the new area is between the curve and the axis. To find, and what we're going to do here is we want to go ahead and try and find the rate of change of this area. How can we find how fast this area is changing? Well, we do that the same way we find any rate of change. We just take the derivative of both sides with respect to the input. And what is the input here? The input is x. And so we go through and we say, okay, let's take the derivative of the area function. Whatever we do to one side, we better do that to the other side as well, right? Okay. But then we also know that the derivative of this, and this is just like the opener for today, really means the derivative of this. It's just the fundamental theorem of calculus, isn't it, that we learned last class? And we can take the derivative of this last piece quite easily. The derivative of capital F of x, the derivative of capital F is the antiderivative. You take the derivative of the antiderivative, it just becomes lowercase f of x. F of a, might be worth writing, is a constant, right? This is a constant down here, and that is 0. So we end up just getting f of x. Now, what does that tell us? Well, what it's telling us here is that if we have a constant to x on our limits of integration, then the function that tells you how fast the area is changing is just the function of which you're finding the area. Which some people go, well, yeah, of course, and others go, oh, wow, that's actually pretty fascinating. So whatever function is here is going to tell you how fast the area is changing. And so when we saw that up above, right, when we had part B a constant to the x power, and they said, I want you to find the derivative of all this, there's a shortcut here, because it is just the function that's inside, albeit with the upper limit plugged in. And that's it. We didn't have to go through this step, or this one, or this one. We can skip straight to the answer. All right, filling in down here. The derivative really just seems to undo the integral. And that should also make sense, right? Because the integral is the antiderivative. The derivative is the derivative. Derivative, antiderivative, undo, and just leaves us with the function. You do have to remember to plug x in, though, because although this is a nice shortcut, realistically, you are still going through all of the steps in this problem. And so I find it helps if we start off with all of this just so we can see the intermediate steps that we get to skip. We had to take the antiderivative. We had to substitute in x and substitute in 1. That's why our variable gets changed, and then take the derivative from there. Cool. So what happens if your limits are switched around? Well, let's just go through all the steps again, and hopefully in the future you can just skip this, but going through all the steps here, we do the antiderivative, so it becomes capital F of t from x to a, and we're still trying to take the derivative of that. And then we're still looking to take the derivative, but it's capital F of a minus capital F of x. What's a constant here? Oh, that guy right there. So that one is 0. And then the derivative of capital F is lowercase f of x. And so we end up with negative f of x. All right, so if we're going from a constant to the variable x, the function that shows you how fast the area is changing is lowercase f of x, the function inside. If you switch the order, then it just becomes negative f of x. You also could have seen that earlier on, right? We could have seen that, I'll use the space over here, by just changing the order of the limits, right? We put a down below, x up above, f of t dt, and now this matches the fundamental theorem part 2 that we did up above, and you know that the answer is f of x. But where does that extra negative come from? Oh yeah, whenever you flip the order of integration, you have to negate or make your answer the opposite sign. Okay, last but not least, we're going to take a look back at problem C from the opener because that didn't quite follow the same pattern, right? We've been using x as one of our limits, but instead of x, let's use a more generic function, g of x, where g of x can stand for x squared, g of x can stand for natural log of x, g of x is just a function. It could stand for x if we wanted. So let's go ahead and try this pattern using g of x. I'm still going to use a constant down here because it's pretty easy to make the jump to part C, but we will do that to conclude today anyways. So alrighty, we have the antiderivative of lowercase is capital F from a to g of x equals, and then we have d dx of fundamental theorem f of, we're replacing t with g of x, and then t with a. Okay. And then we're looking for the derivative of all this. We'll do the easy one first. Capital F of a is a constant, no problem there. But let's go ahead and do the first one. The derivative of, oh, this is a chain rule problem, isn't it? We do the derivative of the outside first. The derivative of capital F is lowercase. Keep the inside the same, which means we need to multiply by the derivative of the inside. And so this gives us the more commonly stated second part of the fundamental theorem of calculus. It gives us a way to easily measure how fast the area beneath a curve is changing and look at how it ties everything together with area and rate of change or derivatives in the same problem. If you want the shortcut, which you should because there are some problems where you can't do the antiderivative, we'll see this shortly, to calculate this, it's very easy. You keep the inside function the same, or you keep this the integrand the same, f of, except you need to replace this with your limit of integration. But then there's one last trick here because there are all of these steps in the middle and you technically have to do the derivative of what you substituted in. We do need to multiply by the derivative of the inside. So I'm going to quickly revisit the third problem on the opener and then we'll do a couple examples and that's it for today. Okay. Looking at this opener over here, can we see where this answer came from? Okay, we're going to try to come up with it without doing any of the extra work. They want the derivative of this. That's easy. We start with the upper limit and we keep this the same. So it becomes sine of x. Technically, after you plug in x, you should multiply by 1 because it's the derivative of x. Then we subtract the lower limit, but it still becomes sine of the x squared gets plugged in. And then this is our fundamental theorem of calculus part 2. We have to multiply by what we plugged in. We've evaluated an x squared, so this becomes a 2x. And this guy should match what we got down below. Now, I know you're probably looking at this going, well, why are you showing this shortcut? It's a pretty easy thing to do. You just do an antiderivative, plug them in, then take the derivative. I probably don't need a shortcut. And you're somewhat right. With some functions like sine that we did on the previous page, finding the antiderivative is pretty easy. But what if we looked at something like this? And then you didn't know the shortcut. And you're like, okay, well, what I want to do here is I'm going to take the antiderivative of sine squared. And then you run into a bit of an impasse because we don't know how to find the antiderivative of sine squared. You can play around with it. You can try to take the derivative of anything you get, but I think you'd be hard-pressed to come up with that antiderivative. But we can still, even if we're not sure how to take the antiderivative and measure the exact area, we can still explain how the area is changing. And that is our fundamental theorem of calculus part 2. How does it work? We take the sine squared of whatever piece, The 1, if you were to substitute in, well, no, we'll do that second, and we substitute in the upper limit. Then you multiply by the derivative of what we substituted in. Minus, now if we look at this second part, this is just a constant, and when you do the derivative of a constant, it's just 0. So what is this final answer? It is just sine squared of x. It is exactly the same as the integrand part of this integral, just with x instead of t. And that's all there is to it. Okay, let's try another. Example 2, take the derivative of the integral from x to 5 of that stuff. Well, if you substitute in the upper limit, that's going to become a constant. 25 plus 1 is 26. Whatever the antiderivative is, we don't know that one. The derivative of a constant is just 0. Fundamental theorem minus, now we just substitute in the lower one, x squared plus 1 times the derivative of what we substituted in. We substituted in x, so we multiply by 1. I know you're going to be tempted to multiply by 2x or even the derivative of all of this, but it's just this guy that we're taking the derivative of. And so this becomes negative x squared plus 1. And you might have even been able to get from here over here even faster if you just realized this was the only variable. It was on the bottom, so it's going to be negative. Okay. Last example. Take the derivative of this guy. Now we're doing okay. Cosine of, there is nothing for t, but there's still a square. And then 0 is just 0, so you can put a minus 0 at the end if you wanted. Doesn't really matter. We need to substitute in x squared for t, and then multiply by the derivative of x squared, which is 2x. Finishing this off, this becomes, we'll put the 2x in front, that's our convention, 2x times cosine of x to the 4th. Again, you're going to be tempted to say, wait, this is x to the 4th, shouldn't we multiply by 4x cubed? No, it's whatever the limit was that you plugged in. So the rest of today is really going to be you guys seeing these problems in action. The majority of these don't use equations that we actually are given. The majority of these are based off of graphs. That's the way the AP exam likes to present them. So you really have a bunch of pages that have graphs given to you, and they're going to ask you to analyze those graphs. And I think on pretty much all of these, you're going to be asked to use the Fundamental Theorem of Calculus Part 2 that we just practiced here in some way, shape, or form. I am going to do these 2 examples with you, but you should notice that they all have a year and a question number attached to them, and I think I set them mostly to go from oldest to newest. Might have switched some around based on space, but that means you can look them up, right? Because any free response question that's public knowledge can be looked up online. It's on the College Board website, and those are really going to be anything from, like, I don't know, 2010 and earlier, and there's even some later than that that are free. They release all 6 of the free response questions every year. There are some secure ones that you can't access, but you should get 6 new ones every year. And I would suggest, if you really want to be good at this AP exam, start back at 1999, maybe 1998 if you want. That was when the big revision of the AP exam happened, and just work every free response from 98 up to present day. You do that, you'll slam dunk the test. It does take a bunch of time though, but that is what I did when I first started teaching this class, and I felt way more confident after doing it. So let's get started. 1999, question 5. The graph of the function f, we should probably label this, consisting of 3 line segments. We see those is given to the right. Let g of x equal the integral from 1 to x of f of t dt. I'd like to analyze that before we even look at any of the questions here. So what is g of x? G of x is not the graph. G of x is saying it's going to measure the area between the graph of f and the x-axis starting at 1 and going to x. So maybe we should look at the very first problem so we can try to put some visual to this. So they're going to ask us for, and I'm going to split this into 2 pieces here, because they're asking us for both g of 4 and they're also asking us for g of negative 2. I've found in the past that usually the first one takes less work and the second one takes a little bit more work or is a little bit trickier. That's a very soft rule, more like a guideline, but that's what I've seen over the past few years. So g of 4. Well, that means they replaced the x with 4, so we should replace the x over here with 4 as well, not t. That's an x value, so we're just going to replace the x with 4. So what is g of 4 created by? G of 4 is created by measuring the area from 1 to 4 beneath the graph of f of t dt. So here's 1, here's 4, and they want the total area between the graph and the x-axis. So that area would be all of this over to here. And I always like to think of the area that starts at 1 and it starts moving to the right, right? We're adding on area until we get over here, yeah? So how do we find that area? Well, this is why I told you earlier when we did all those approximations, it was not a waste of your time. You're still going to be doing plenty of approximations. This isn't even an approximation. This is all geometry, isn't it? So there's plenty of ways you can do this. I'd probably subdivide here. And the reason I'm doing that is because this area, 1 by 1, is just 1. This one is a triangle, 1 times 1, 2, 3, isn't it? So this is a height of 3, base of 1. Base times height divided by 2, that gives us an area of 3 halves. And then what about these last two? Well, although this is half, it's half of the square, and this is also a half, we should realize that this triangle is below the x-axis, so it's negative 1/2. In fact, I probably would have looked at these two and said, oh, they cancel each other out. One's positive, one's negative. So if you really wanted to write out what g of 4 is equal to, you could have shown all of the work for this, right? You could have said it's going to be 1, that's this guy right here, and then add on the 3 halves, add on the 1/2 that was down here, and then subtract off the 1/2, but that just seems like overkill to me. So finishing this off, 1 plus, let's call this 2 over 2 plus 3 over 2, I'm looking at 5 halves. All right, now we look at the other. G of negative 2, the integral from 1 to negative 2 f of t dt. So we are again starting at 1. But this is weird because now they want us to accumulate area up to negative 2. But negative 2 isn't forwards, negative 2 is backwards. And so I would really suggest if you get something like this that you switch your limits of integration. I think it'll make your life a little bit easier. So we'll go negative 2 to 1 f of t dt. And then don't forget the negative out front, the biggest cause of missing points on problems like this. Okay, so we're going from, now we're starting over here, from negative 2, we're going over to 1. That's just one big triangle. How exciting. 1, 2, 3, so a base of 3, height of 4, and we're doing 1/2 of that. So negative, we're doing 1/2 of the base times the height. So half of 12 is going to be negative 6. And looking at that, that might be a little bit weird because you're like, wait, this area is above the x-axis. And you're right, but that area is still negative because technically they wanted us to find the area moving backwards. And one way you can think of that is the area was already there. That's not an easy way to do it. What is a good way to do this? I'm trying to think about how I can use my pen here. There we go. So the area is already there, and you're moving backwards and like erasing that area. So it's like you took away 6 area units. Another way you can think of it is if you moved backwards, this is negative 3 times 4. But regardless, if you rewrite your limits going from smallest to biggest, you need a negative there, you end up with a negative 6. Cool. Well, that's all fine and dandy, but we didn't actually do anything new there. You could have done that like 8 classes ago. I think I mentioned the Fundamental Theorem Part 2 that we just learned should come in somewhere. Where is that? Oh, there's a Part B. Find the instantaneous rate of change of g. Okay, well, we know g of x, we're going to want to leave a little space here, is equal to this guy. Instantaneous, how fast is something changing at a specific x value? That sounds like a derivative to me. So we need our, we'll use blue, d dx of each of these. Okay. d dx of g of x is just going to give us g prime of x. d dx of this guy, here it is, Fundamental Theorem Part 2. We're going to keep the inside the same, so it's f of something. There's only one variable here, the x gets substituted in. Technically, then we multiply by the derivative of x, but that's just 1, so I think no reason to do anything. The other limit is a constant, and we know the derivative of a constant is 0, so there is g prime of x. Exciting. However, they didn't just ask what's the instantaneous rate of change of g. They said at x equals 1. So if we want to find that, we're going to go through and we're going to say, let's find g prime of 1, and that is going to be found by doing f of 1. I always like to keep writing g prime so that I don't lose myself in all the different variables here. So g prime of 1, what is f of 1? Well, if we look at the graph up here, this is the graph of f, and f of 1 is 4, right? F of 1 is 4. You input 1 into your function called f, and you get an output of 4. And we're done. What does that tell us, though? Technically, it tells us at 1, the area, or g, but g is the area between the graph of f and the x-axis is increasing by 4. So right when we're here, we've just increased by 4, which makes sense. I mean, this is like a height of 4 right here. Think of it as an itty-bitty little rectangle, right? So it increased by a height of 4. Let's say the area was right over here. You had this much, and then you just wanted to tack on just a little bit more. That's the increase that we're talking about right there. Okay, we'll try one more, and then you guys have the rest of these to finish off on your own. All right. Graph of function f shown to the right consists of 2 line segments. G is this function. They love defining G to be an area or accumulation function. They're asking us for 3 items here, so I'm going to split this into 3 pieces, like so. Hopefully that's enough room. Let's start with G of negative 1. So g of negative 1 is equal to the integral from 0 to negative 1 f of t dt. I don't like that it goes from bigger to small, so I am going to switch that order. So now along the x-axis, we're going from left to right. Then I'm going to take a look at this graph. We're going from negative 1 to 0, and the only area that's there is this triangle. So I think g of negative 1, don't forget the negative, will be 1/2 a base of 1 and a height of 3. So to me that looks like g of negative 1 is negative 3/2. 2 to go. Next we want g prime of negative 1, and this step is actually pretty important. I should have mentioned it before. Some of you could see in your heads the answer to g prime of negative 1. You can say, oh, I know I'm going to do a derivative, I know I just plug it in, and I know it's going to end up being, in this case, 0. If you just put 0, you will almost always miss a point, because now you are using a function called g prime that they did not give you. You can never use a function that's not given to you, the same way that you can't reference a graph that's not given to you, right? If you're only given the graph of f prime, don't start talking about f double prime. If you're just given g of x, don't start talking about g prime. But you can get around that by finding the function for g prime of x. All right, how much work do you have to show? You can literally just write what g prime of x equals. However, I'm going to show that extra step of where it comes from. I think that's not a bad idea, but no one would necessarily expect you to show this middle step. So we're going to do g of x, the integral from 0 to x, f of t dt. They're asking us about g prime, so we do need to show the derivative of g ddx ddx. Okay, this will give us g prime of x equals, well, it's an easy function, it's just f. We substitute this in, and it's just f of x. Great. Now we've defined the function g prime. Now we can actually evaluate something into that function. So g prime of negative 1 is going to be f of negative 1. Here is the graph of f. Where is f of negative 1? Right there. F of negative 1 is 0, so g prime of negative 1 is 0. But you see how I kept g prime on the left side the entire way through? That way we don't start just running things onto each other. I really like just showing one equal sign, not more than one, and just working from top to bottom. You don't have to do that. No one's expecting it of you, but it's not a bad thing to be very clear about your work. Last but not least, g double prime of negative 1. Well, same idea. We should probably find g double prime of x before we start using it. So we'll start with g prime of x. How do we go from g prime to g double prime? We take the derivative again. And again, writing this ddx is maybe a little bit extra, but I don't think it's bad for you. G double prime of x is equal to f prime of x. They are interested in g double prime of negative 1. And in order to do that, we find f prime of negative 1. So to find g double prime of negative 1, we're looking for f prime of -1? We already have this, but what does f prime measure about this graph? Oh yeah, f prime measures the slope, and this is a line segment, so with slope I'd probably just count. Looks to me like we go up 3/1 to get to the next nice point, and so we can say it's 3/1 or 3. I think at this point you probably have enough to go through and do the last 2 pages of this. You'll notice that we start to get later and later in time, but we only get up to 2006. That was actually the year I took the AP exam. Very exciting. You can figure out my age right now. I distinctly remember this problem because I knew I got it wrong when I left the test. I figured it out afterwards. I was like, oh yeah, definitely forgot this piece, and then I was sad. But I still passed the AP exam, so oh well, a positive memory overall. Good luck on this. I'm excited to have you back next class where we learn our last theorem for the year, and we have our last video for this unit. Right? Clock's counting down. We're getting closer and closer to that AP exam. So thanks for sticking with me. Keep up the great work.